If you hear healthcare desert, do you imagine a place that's too hot or barren? But a desert, by definition, simply lacks water or resources, in this case, healthcare access. Traditional GIS has long been used to help relieve healthcare deserts by identifying ideal locations for new facilities through spatial analysis. However, I reviewed a study that takes site selection further, introducing an innovative machine learning approach that breaks from traditional methods. While classic GIS relies on established spatial techniques, this model combines geospatial data with computer vision to capture complex spatial patterns at multiple scales, enabling a flexible, scalable solution. Unlike traditional approaches, it can adapt quickly to different regions without extensive manual adjustments, making it an ideal tool for addressing healthcare gaps in diverse environments. This study aims to improve healthcare facility planning by leveraging advanced machine learning on spatial data. It highlights the limitations of previous methods, such as manual local specifics selection, and emphasizes the need for a scalable approach. The researchers used a multimodal AI to select sites, combining several geographic features like population density, land cover, and road networks. They converted vector data, like the roads, into raster for analysis, raster data. They also curated a healthcare facility data set from OpenStreetMap and used it as a prediction baseline. Their model achieved impressive accuracy in predicting suitable locations for healthcare facilities, using Ghana as a case study. The model's high both recall and precision is a significant step towards scaling this approach globally. Their model could inform healthcare infrastructure planning worldwide, identifying optimal locations based on data-driven insights. The study aimed to develop a scalable and generalizable approach to healthcare site selection. Using a multimodal machine learning model overcomes many of the challenges of traditional methods, offering a solution that can adapt to different country contexts without extensive manual tuning. The authors use a variety of geospatial data sources, including population density data from WorldPop, which is crucial for understanding the potential demand for healthcare services. Land cover data offers insights into land types, which is essential for understanding which areas suit construction or not. Road network data from OpenStreetMap provides accessibility information, which is crucial in determining the ease of access to healthcare facilities. Elevation data also helps assess areas that might pose simple construction challenges. They transform the vector layers into raster layers for machine learning analysis, allowing the model to see spatial patterns as it would with image data in computer vision. The authors developed an attractive geospatial machine learning pipeline for their methods that combines multiple feature layers to classify areas for healthcare suitability. They processed each geographic feature as a raster layer and stacked them by location to do this. Stacking raster layers is important because it effectively combines spatial features or a robust predictive model. This method of transforming geographic data into visual data and processing it through a machine learning model is relatively innovative. In the Earth observation field, we call this concept of stacking raster layers for machine learning training data a data cube, or sometimes I hear the term deep cube. So you have multiple data layers stacked along the z-axis to go along with your spatial x and y axes. One of the data layers is the phenomenon you're trying to predict, like the location of healthcare facilities. And this methodology is gaining popularity in geospatial AI because the model can learn some spatial relationships, and machine learning works really well on images or raster data. The study uses LightGBM with early stopping as the classifier. LightGBM is a fast and efficient machine learning algorithm that uses decision trees to make accurate predictions boosted on the most critical features. It is excellent for handling large data sets and complex patterns. Early stopping means the model stops training once it fails to improve or fails to learn more, and this prevents overfitting. You want to avoid overfitting a model because it means the model will only work on the training data and not generalize to larger data sets. The model was trained and tested with data from Ghana, using various local features to generalize suitability patterns. LightGBM combines many small models to improve accuracy by correcting previous errors. This approach is well suited for complex site selection tasks because it effectively captures intricate spatial patterns and makes precise predictions about suitable healthcare facilities. The model accurately identified suitable areas with high recall and precision scores. Specifically, it demonstrated a 94% recall and 98% precision. This leads to an impressive F1 score of 0.96. Here, the researchers introduced a simple but clever approach to site selection that uses false positives. False positives are locations where the model predicts a healthcare facility should exist, but none currently does. They saw false positives as indicators of suitable sites for new facilities. This method leverages model errors to identify potential areas for expansion, turning what data scientists would traditionally see as a mistake into valuable, actionable insights. It's a fascinating concept that reimagines how predictive models can support decision-making by uncovering opportunities that are sort of hidden within the model's limitations. This paper contributes a new approach to healthcare site selection, combining traditional spatial analysis with modern machine learning in a way that scales and adapts across different regions. Its critical contributions include, first, a novel data processing pipeline that transforms geographic data into visual data, making it suitable for machine learning models. Second, they accurately identify potential healthcare facility sites validated by a case study in Ghana. Third, their model is generalizable to other countries, providing a valuable resource for global healthcare planning. Contrary to the advances in this research, a critique of their approach is that it relies on the locations of existing healthcare facilities to predict where new ones should go, which somewhat assumes the current placements are ideal. However, this may not reflect actual healthcare needs, as some facilities may perform better than others. To address this, the model could incorporate data on each facility's effectiveness and success to enhance accuracy in site selection. If you are leading efforts to alleviate some of our healthcare deserts, I'm sure you face challenges in accurately identifying optimal sites for healthcare facilities, especially in resource-limited regions. With my expertise in geospatial AI and public health, I can help by creating data-driven models that consider local demographics, accessibility, and infrastructure to guide site selection. I offer tailored consulting and partnerships to help organizations and businesses implement scalable, impactful solutions that optimize healthcare access and resource allocation across regions. While the model is impressive, we could improve it in multiple ways. First, including additional dimensions like travel time and healthcare needs specific to different demographics would make the suitability analysis even more targeted. Adding many variables takes more advantage of using AI, since this is something AI does better than manual analysis. Perhaps the first variables we could add are more detailed demographic data, such as age and income, which could further refine the site selection process, making it even more helpful for local healthcare needs. Second, the model can be applied to more varied geographic locations to test its adaptability across diverse terrains and population distributions. We can even use an interactive process of adding and evaluating the model in more geographic locations, thereby making the model more robust and generalizable. Third, adding cost analysis or feasibility assessments for site construction would be valuable for practical decision-making. It is one thing for the model to say we should add a healthcare site to a location when it might be far too costly to construct it. What's new here is the approach to geospatial data processing, converting vector data into visual images for use in a machine learning model. This innovation combines the strengths of computer vision and spatial analysis, allowing the model to see and understand spatial patterns. One thing that is not new is the underlying machine learning model, like GBM, which data scientists commonly use. However, using a tried and true model is not necessarily a bad thing, since it gives credibility to the results. Companies working with healthcare infrastructure, nonprofits, or government agencies could use this model to streamline planning and improve resource allocation, ultimately reducing operational costs and increasing impact. This model opens new avenues for integrating computer vision with spatial analysis. This scalable approach can be applied beyond healthcare to areas like education, infrastructure planning, certainly business. By combining business data like competitor locations, profitability, demographics, and customer demand into a multimodal AI model, companies such as restaurant chains, banks, retailers can accurately predict ideal new locations. This approach's scalability means it can be applied globally wherever data is available, elevating site selection to a new level of precision and efficiency. So let's imagine a scenario where a restaurant chain, a coffee shop chain, a bank, or a company that owns real estate uses data on their existing assets, and instead of simply selecting a site in a local area, finds optimal locations throughout an entire country or beyond that can produce a successful new store or branch. This model streamlines planning, optimizes resource allocation, and maximizes impact by reducing operational costs and enhancing decision-making for companies, nonprofits, and government agencies. This model is particularly valuable for low or middle-income countries with limited healthcare access. Governments and NGOs can make data-driven decisions to improve access to essential services by identifying the most suitable locations for healthcare facilities. This research aids decision makers in government health, global health organizations, healthcare networks, urban planning, and private investment by providing a data-driven model to identify optimal locations for healthcare facilities. It enables effective resource allocation and improved access in underserved areas, making it a valuable tool for strategic expansion and impactful healthcare investments. A team led the study from several respected institutions, including the Virtue Foundation's Actionable Data Initiative Research Group, Manhattan College, Harvard Medical School, and Data Robot, among others. The collaboration between these organizations emphasizes the multidisciplinary nature of the research. The researchers published their paper at IEEE International Conference on Imaging Systems and Techniques. IEEE is renowned for its high-quality, peer-reviewed conferences, which underlines the scientific credibility for the paper. This paper introduces a powerful new tool for healthcare facility planning. The authors have created a highly accurate and scalable model by combining geospatial analysis with machine learning. This approach can potentially guide healthcare development in underserved regions and lays the groundwork for future advancements in geospatial machine learning. This model is an excellent example of how technology can improve people's lives by making essential services more accessible. Thanks for watching. If you want to learn more about how data science transforms healthcare, stay tuned for more videos. Thanks so much.